Hello, hello. All right, this video I'm going to be talking about bond types. There are four main bond types that you need to know, and I'll tell you now that these two are the main two that we are going to be working with throughout the year. But I need to talk about these two first. Now, the first and most important thing you have to know about these two bond types is they're not real bonds. Okay, there is no physical connection that actually holds atoms together in these two bond types. Okay, there is a physical connection that connects these two. These two are more, they act like bonds, and so we call them bonds. Okay, so you need to know first and foremost that metallic and hydrogen bonds are not real bonds. Now, they are not real bonds for different reasons. Okay, first off, a metallic bond is going to be a bond between two metals. That is, when you mix two metals together. So this is properly called an alloy. Okay, so anytime we mix different metals together, for example, bronze or brass are alloys that we get from mixing, I think, zinc and copper. History people, you'll have to correct me on that if I'm wrong. Mix zinc and copper to get bronze in different proportions to get brass, I think. And it really just comes down to, it's not a real bond, it's just the atoms are mixed up well enough that it acts as a different material. And so what happens is, instead of being the properties of zinc or the properties of copper, it kind of walks the line between them. And so the more zinc you put in, the more zinc-like properties it has. The more copper you put in, the more copper-like properties it has. But it tends to kind of shift back and forth depending on how you actually mix them. This is more like mixing paint. Okay, if you mix yellow paint and red paint, if you mix more red, you're going to get a darker orange. If you use more yellow, you're going to get a lighter orange. That's how metallic bonds really work. It's not that they're actually connected so much as we've just mixed them up well enough that their properties start to mix up some. You can usually separate these back out if you've got a mind to do so. It's not quite so simple as this makes it sound, but if you melt them down, you can usually separate them back out fairly easily. Hydrogen bonds are most often exemplified by water. Now, you guys talked about hydrogen bonds at least briefly at the beginning of Biology 1. I know you did this year, those of you who are in biology this year, and I assume that you did last year for the juniors in the class who had biology last year. But hydrogen bonds, they're not real bonds. It's the result of the fact that water, which is H2O, so we have an oxygen bonded to two hydrogen atoms. Oxygen tends to collect electrons, and so because of that, this end of the molecule tends to end up negative, while this end tends to end up slightly positive. And so because of that, hydrogens from other water molecules end up attracted to the oxygen end of some of the water molecule. Different, that's what I'm looking for. The hydrogen end of some water molecules end up attracted to the oxygen end of other molecules. That's the phrase I was looking for. However, water is not the only place we see this. We also see this in DNA and in macromolecules like proteins. Hydrogen bonds determine how they fold and twist to make sure that they do so in the proper way that they can fulfill their function. Proteins have to be able to bond or wrap around certain structures in order for them to work properly. Hydrogen bonds make sure that as they are produced, they fold up properly so that they end up in the right shape to be able to fulfill their task. Hydrogen bonds are incredibly weak. But you put enough of them together and they tend to act pretty strongly. And like I already said, in macromolecules, they tend to hold those things together or keep them in the proper shape as they're rolled up. Now, the two really important molecules is not the right word. The two really important bond types that you have to be able to pick out are ionic and covalent. The simplest explanation of this is that in an ionic bond, you have a metal and a nonmetal. Now, that is not always the case. Sometimes it's just two different ions. So let's say this tends to be our formula for ionic. We have a metal with a positive charge and a non-metal with a negative charge. These become attracted to each other because they have different charges, so they stick together. Now, the nonmetal can be replaced with a polyatomic ion with a negative charge. Occasionally, ammonium can take the place of the metal, but that's a lot less common. Most polyatomic ions have negative charges, so we tend to see them. But this is kind of your general formula. A metal and a nonmetal means you're talking about an ionic bond. Already said that. Officially, the definition is between two ions, but frequently you'll see a metal and a nonmetal. A fundamental difference: in an ionic bond, electrons are actually transferred from one atom to another. So your metal comes along, and remember, our metals always want to lose electrons. That should ring a bell from the last unit. And our nonmetals are hanging out. They really want to take electrons from somewhere. So our sodium ion, which has one electron, floats up, and our chlorine atom is hanging out over here, and it needs one electron. It wants to gain one electron. So chlorine will reach out and grab this electron and pull it in. And what that ends up doing is the sodium now has a positive charge and no electrons, while the chlorine has a negative charge because it has now got 8 electrons. And so these two get stuck together. And that's how an ionic bond works. It's pretty much that simple. Covalent bonds are more cooperative. The co in covalent is cooperate. They cooperate to fulfill their valency needs. Okay, all polyatomic ions are held together with covalent bonds. Okay, this is incredibly common amongst your non-metals. Non-metals covalently bond all the time. Okay, in order for a covalent bond to form, there must be 2 electrons. One must come from each element. And when we start doing molecular Lewis structures, that'll give you a better idea of how this actually works. I'm not going to try and draw one out right now, like I did here. But yeah, in a covalent bond, 2 electrons are required. One comes from each element. In ionic, only 1 electron is required. One donates the electron and the other takes it. In covalent, both are sharing both of the electrons. So that's an important distinction. Okay, covalent bonds are usually fairly weak, especially compared to ionic bonds. Ionic bonds are incredibly strong. Most of the strongest bonds that we know of are ionic bonds. But there are a couple of covalent bonds that I don't know if I would say they are strong so much as they are incredibly difficult to break. An excellent example of this is the carbon-oxygen double bond in carbon dioxide. This is one reason why carbon dioxide is considered to be a very dangerous product, and why it contributes so much to global warming. Because these bonds are extremely difficult to make, to break. They're easy to make. They're hard to break. And it's not because they're particularly strong. It's just there's not a lot of reactions that will cause them to separate, which makes things a little more difficult. Now, on the quiz that you have this week over bond types, any statement on the board here is fair game for the matching section. So you have to be able to pick out you have to be able to match the statements to the bond type that it is describing. You need to know that alloys refer to metallic bonds. And I'm not going to get any more specific on that one. You need to know this information in order to match them with the bond type. That's the important thing. The other half of the quiz is what we're about to practice. I'm going to give you chemical formulae, and you have to tell me whether it's ionic, covalent, or metallic. And so let me pull that up, and then we will continue from there. This is worksheet 3. All right, this is worksheet 3. There is a practice molecule at the top that everybody's going to kind of go through together, and then the rest of these are for you to do on your own. What I want you to do is write out what kind of element the first is, plus what kind of element the second is, equals, and then tell me it's either ionic, covalent, or metallic. So nitrogen is a nonmetal, so we say nonmetal plus. Oxygen is also a nonmetal, so nonmetal plus nonmetal equals, well, that's going to be covalent. And that's it. That's it. You just go through and do that for all of them. So you're going to have to be able to identify the classification of all of your elements in order to do this, which is why that was part of Unit 1. So hopefully you learned your classifications properly, where this is going to be extremely difficult. You have to know the difference between ionic, covalent, and metallic. Most people don't have too many issues with metallic. It's in the name. But covalent and ionic, people tend to get mixed up a lot. So covalent is 2 nonmetals. Ionic is 1 metal and 1 nonmetal. And then metallic is obviously 2 metals. So work your way through this. I think there are 17 of them. Yeah, 17. Identify all 17 as ionic, covalent, or metallic. I do want to look at 11 real quick. Everybody always gets to this one and goes, I don't know, I don't know. I'm going to point out there's a subscript 2 here. So this is 2 different atoms, even if they are the same element. Okay, this is a special type of compound that we will talk about later called a diatomic. But yeah. So this one does have 2. You'll just use oxygen twice on this one. And that's it. This is what we'll be going through on Tuesday after the polyatomic ides quiz, or bell work. So, I'm saying that I'm not going to post this video until after we cover it. So, you'll already know this. You'll already know that by then. So, work on this. Get this filled out. This is your practice. Quiz for this is, I believe, on Friday. Yeah. Friday's your bond types quiz. Hope this helps. Have a wonderful night.